Hi, Assalamualaikum. Okay, guys, as usual, don't forget. Also, okay, thank you. Hi, Assalamualaikum. So let's discuss tutorial 4. Alright, let's start by question number 1. Okay, so the question asks you to sketch the magnetic field line for four different situations, which is for a magnetic bar, for a straight wire carrying a current, for Earth, also for a solenoid. Okay, so I don't want to discuss this because I think the answers given already in the notes. Okay, so just copy and paste. But remember, in sketching this, make sure that there is no floating lines. What do I mean? Here, all the lines should touch the magnetic bar. Okay, there is no floating, no air gaps here, and then no overlapping between lines. Okay, so this is the pattern produced by any magnetic bar, and this is by any straight conductor carrying a current. Alright, and this is the pattern produced by any solenoid. Okay, the pattern of magnetic field, and this is the magnetic field of Earth. Okay, so everything given in your notes, so just check it by your own lah. Okay, now let's continue by question number 1b. Okay, so determine the direction of the resultant magnetic field at point P, Q and R, where point Q is halfway between wire X and wire Y, which carry the same current. Okay, there are two different wires, which is X and Y, carrying a current equal in magnitude, and for this situation, both current just directed upwards. So they ask you to find the direction of resultant at point P, point Q and point R, where Q is the middle point between X and Y. Means that the distance between XQ and YQ are the same. Okay, alright, so by using our right hand grip rules, okay, this is the pattern of magnetic field produced by wire X. Okay, at the left side of the wire, the magnetic field just directed out of page, and at the right side of the wire, the magnetic field just directed into the page. And then for wire Y, still the same, by doing the same thing using our right hand grip rules. This is the pattern of magnetic field produced by the current flow. Alright, so at the left side of wire Y, the magnetic field just directed out of page. Okay, out of page here. And then at the right side of the wire, the direction of B just directed into the page. So into the page. Alright, so for wire X, this is B, at this side out of page, at this side into the page. Okay, and then for wire Y, at the left side, okay, it's B just directed out of page, and at the right side, it's B just directed into the page. Okay, so as conclusion, at P, both B just directed out of page, so the resultant of course directed out of page. At R, both B just directed into the page, so that the resultant also directed into the page because they are directed in the same direction. But at Q, and BX just directed into the page, BY just directed out of page, equal in distance, giving you equal magnitude of B. So one of B is negative, the other one is positive, so they are cancelling each other. Okay, giving you zero resultant. Okay, so the answer just be like this. So this is the way. Okay, so this is B produced by each wire, which is BX, BX and BX, BY, BY and BY again. Here the resultant just directed out of page because they are the same, and here the resultant just directed into the page because they are the same, okay, in the direction. And then for this point, they are cancelling each other because they are equal in magnitude but opposite in direction, isn't it? So at Q, it's just zero lah. Okay, for the next case, okay, we just change the current. Okay, current X now just directed downwards, but for current Y still the same, it just directed upwards. Okay, so what happened to the resultant at P, Q and R? Okay, so again, by using our right hand grip rules, so this is the magnetic field strength produced by wire X. At the left side, B just directed into the page. At the right side of wire X, B just directed out of page. Okay, by doing the same thing for wire Y, using our right hand grip rules, so at the left side of the wire, our B just directed out of page, so out of page. Okay, and then at the right side our B just directed into the page, okay. So at the middle here, still same, Q is the middle point, so equal distance here, giving you equal strength. Alright, but both B just directed out of page. Of course, the resultant, it must be directed out of page lah. Okay, but for P and Q, one of B just directed into the page, while the other one is directed out of page. Still same here, out of page and into the page. But is it equal to 0? We need to check this by using the equation of resultant. Okay, what happened now? This is the way how to check it. Okay, so the answer, they are not equal to 0. Okay, how to find this? Okay, first, at the middle here, of course, we know that Bx just directed out of page, also By, then the resultant, it must be out of page lah. It's quite okay. But for P, Bx just directed into the page, while By just directed out of page. Are they cancelling each other? It's not, because now R are different. So this is Rx, and the distance between point P and Yx, and this is Ry, the distance between point P and Y. So in this case, Rx smaller than Ry, isn't it? So the equation of resultant here is sum of B equals to Bx plus By in vector. So Bx just directed into the page, so it must be negative lah, negative Bx, while By is positive because By just directed out of page. Okay, so we just expand the equation. Bx equals to mu naught Ix over 2 pi Rx, and By is mu naught Iy over 2 pi Ry. So in this case, Rx smaller than Ry, isn't it? Okay, so smaller Rx giving you greater Bx, because B and R, they are inversely proportional. Okay, again, smaller R here giving you greater Bx, and therefore Ry is greater than Rx, so greater R giving you smaller B. Again, B and R, they are inversely proportional, isn't it? So in this case, By is smaller than Bx, where By is positive while Bx is negative. So the negative values is greater now than the positive one. So by having greater values of negative, the resultant should be negative. So at P, it just directed into the page. Still the same for R. Okay, this is point R. So this is Rx, the distance or separation between point R and Yx, and this is Ry, the separation between Y and point R. So Ry smaller than Rx here. Rx is greater. So again, sum of B equal to Bx plus By. So Bx out of page positive, and By is into the page should be negative. Okay. So again, expand the equation. Bx equals to mu naught Ix over 2 pi Rx, while By equals to mu naught Iy over 2 pi Ry. Okay. So again, Ry is smaller than Rx. So smaller R giving you greater B. Greater R giving you smaller B. They are inversely proportional, isn't it? So in this case, By is negative, is larger than Bx, which is positive. So by having greater values of negative, so that the resultant, it must be negative. So that at R, the resultant also directed into the page. So this is the way we need to check the distance actually. Alright, to know are they cancelling each other or not. Okay, next question number 2. Okay, a student is provided with a 3 meters long wire of 0.15 ampere current flowing through it. What is the strength of the magnetic field at a point 50 centimeter away from the wire and at the center of the wire if the wire is bent into a circular coil? Okay, for the first part A, we are talking about a wire. There is a wire. So they ask you to find the strength of B at point which is 50 centimeter from the wire. Okay, so this is B produced lah. So they ask you to find where the distance here is 50 centimeter. So what is the strength of the magnetic field? Okay, so it's quite simple. By using the equation of B equals to mu naught I over 2 pi R, mu naught just a constant, I is the current carried by the conductor, which is 0.15 amperes. 2 pi just a constant, and R is the separation between wire and the point, which is 50 centimeter. But remember, for any calculation, we need to convert it to be in meters, so that 0.5 meters. Okay, substitute the values into the equation, then you will get the answer, which is in Tesla. Okay, it's quite easy. But now for B, we have changed this straight wire to be into coil. Okay, so remember, this is the length of the wire. Length of the wire given is 3 meters. Length of the wire. But now we just bend this wire to be a coil. So remember, length here, this is S, isn't it? So in this case, S still equals to L because we are using the same wire. We just bend this wire. So the total length here still equals to the total length here, which is 3 meters. Okay, so in this case, we need to find R. Okay, so how do we find R? Using the equation of S equals to R theta. Okay, so S still equals to length given, which is 3 meters. R, we need to find it, and theta is the total angle here, which is 2 pi radian. Okay, so this is the question actually. S equals to R theta. Okay, sorry, S equal to 2 pi R. Sorry. So this equation is 2 pi R equals to S. Okay, by using this equation, we just find R first, and then by using the coil equation, which is mu naught I over 2R, this is the strength of the magnetic field of any coil which is at the center. Again, mu naught just a constant. I is the current carried by the wire before, which is 0.15 amperes. Alright, then this is our R. So R getting out is 0.48. Substitute into this equation, then you will get the answer. So remember, this is the hidden info, where the length for this circle still equals to the length of this straight wire. Okay, because we are using the same wire, we just bend it into to be in coil. Okay. Alright, next question number 3. Okay, for question number 3, first, what do we have? Okay, so this is number of turn, which is N, and then this is our length, which is L. So by giving you the number of turns and length of the wire, they ask you to find the current. What is the current? Okay, so they ask you to find the current I that flows in the solenoid in order to produce a magnetic field of, okay, this is the magnetic field strength B, okay, at the center of the solenoid. Okay, so by giving you the strength of magnetic field, the number of turns, and the length of the solenoid, they ask you to find the current. Okay, this is at the center. Okay, because we know that for any solenoid, we have two different value of B, isn't it? Which is at the center of the solenoid, also at the end of the solenoid. Okay, for the second question B, they ask you to find the current produced by the same magnetic field at the end of the solenoid. So the equation are different. Okay, so how is it? Okay, so as we know, magnetic field at the center for any solenoid is B equals to mu naught Ni over L. So this N representing number of turns, this is the length of the solenoid, and this is the current. We need to find it. Mu just a constant, and B given already before, isn't it? 2 exponent -3, so that you will get the current, which is equals to 2 ampere. Okay, so this is the values of B at the center, and as we know, at the end of the solenoid, the values is half than this. That is why the equation is B equals to mu naught Ni over 2L. See, we got 2 here, because the equation is half mu naught Ni over L. Okay, so this is the equation. Again, B given already, mu just a constant, and given is 1200, length also given, which is 1.5 meters. Substitute, and then you will get the current, which is equal to 4 amperes. Okay, next question number 4. Alright, listen carefully for this question, because I think it's really tricky. Okay, we have some hidden info here. Okay, so what do we have now? First, okay, the figure shows a long conductor. This is our long conductor placed near a loop. There is a loop, so we have two different conductor, which is a straight conductor and a loop with radius 8 cm. Radius given is 8 and carrying a current of 1.2 ampere. Okay, so now the current here, let's say this is I2. I2 is 1.2 ampere, the current carried by the loop. If the straight wire carries a current, okay, that one is I1. So I1 given now is 2.4 ampere. Alright, I1, and this is I2. What is the field at the center of the loop? Mu given is 4 pi exponent to 7 Henry per meter. Okay, so as we know, we have two different current, which is I1 also I2. By having two different current, there must be two different B, which is B1 produced by I1, also B2 produced by I2. But now they ask you to find the field, the magnetic field at the center of the loop. Okay, first, at this point, this is a point, they ask you to find the magnetic field strength at this point, which is at the center of the loop. First, B produced by the loop itself, here. And then B produced by the straight wire, also exerted, here. So there must be two different B, which is B1 produced by I1, or straight conductor, also B2, which is produced by I2 or by the loop itself. Okay. Alright, so we need to check the direction first. Are they just directed in the same direction or not? Equal in direction, we just total up the values, which is B1 plus B2. If they are just opposite in direction, one of it should be minus lah. Okay, so how to do that? Okay, first, let's check by using our right hand grip rules. Okay, we need to find the direction of B produced by the straight conductor. Okay, the current is downward using our right hand grip rules. So at this side, B just directed to the pitch, and here B just directed out of pitch. Okay, so this is B produced by the straight conductor. So here is into the pitch, and here is out of pitch. Okay, so this is B1. Okay, so seems like B1 exited on this point is the blue one here, which is directed out of pitch. So B1 is positive, and because B1 just directed out of pitch, and because the loop located at the right side of the straight conductor, at the right side of the straight conductor, our B just directed out of pitch. Okay, so at the center here, still the same. Our B, which is B1, still directed out of pitch. So B1 is positive. At the same time, the loop also carrying a current, where the current just flow in clockwise direction. Okay, by using our right hand grip rules, the forefinger now representing our current flow, and the thumb finger representing our north pole. Okay, so by using our right hand grip rules, we may say that the magnetic field now just our thumb finger just directed into the pitch, isn't it? Okay, so that at this center, B produced by the coil just directed into the pitch. So that one is the B2. So B2 is negative because it just directed into the pitch. Okay. Alright, so we just calculate B1 and B2 separately first. Okay, so B1 is B by straight conductor. So for any straight conductor, the equation is mu naught I over, this is B of the loop. Okay, loop B2 lah. We just calculate B2 first. So this is B2, which is B2 equals to mu naught I over 2R, so that you will get the magnetic field strength produced by the loop, which is at the center here, the red one, and directed into the pitch. So this is B2, correction, B2. Okay, and then we just calculate B1. Okay, so B1 is under straight conductor, so the equation is B equals to mu naught I over 2 pi R. So the current given already also. R, what is R? Okay, before that, for the coil, R equals to radius of the circle given, which is 8 centimeters, isn't it? So 8 exponent negative 2 meters. But now the separation between center and this conductor is 8 plus 4, giving you 12, isn't it? The total distance here is 12. 12 centimeter equals to 12 times 10 to the power negative 2 meters. Okay, so substitute mu, which is a constant, the current carried by the straight conductor, and then also the separation, then you will get the answer, where the direction is out of pitch. That one is B1, sorry, B1. This is B1 and this is B2. Okay, so by getting this, we just calculate the resultant. Okay, I don't like to use this. Okay, I want to show you this. Resultant of B equals to B1 plus B2 in vector. B1 is directed into the pitch, so it must be negative. B2 just directed out of pitch, so it just positive. So we just total up the values, and then you will get the negative answers. So the resultant just in negative means that it just directed into the page. Okay. Okay, so let's turn to question number 5. Alright, for number 5a, what do we have? Okay, determine the magnitude and direction of the force on an electron traveling 8.75 exponent 5 meter per second. So this is v, speed. Okay, horizontally to the east. To the east means that to the right. Okay. In a vertical upward magnetic field. Okay, so B given now, this is B, the magnitude is 0.75 Tesla and its direction just upwards. Okay, so the speed just directed to the right and B just directed upwards. So they ask you to find the magnitude and direction of the force. Okay, so the charge of electron given is 1.6 exponent -19. Don't forget that electron is a negative charge, so by using our right hands rule, okay, we need to refer to backhand, isn't it? Because electron is a negative charge. Okay, so this is the situation. B just directed upward, the speed just directed to the east, which is to the right. Okay, so by using our right hands rule, or by using our palms rule, okay, by using our palms rule, so B upward, our forefingers just directed upwards and our thumb fingers just directed to the right. So our backhand now just directed into the page, giving you F to be into the page. So this is F. Using our right, by using our palm rules. Okay, so seems like this is the hand. I don't know how to draw the hand, something like this. And this is our thumb finger. Okay, so this is I, and this forefinger now representing B. So backhand now just directed into the page, isn't it? The backhand now representing our F. Okay. Alright, so to calculate its magnitude, FB equals to QVB sin theta, where theta is the angle between V and B. So V and B, they are perpendicular to each other. So the angle is 90 degrees. Sin 90 giving you 1, isn't it? Which is maximum. So that Q given is 1.6 exponent -19. The speed also given, and also the strength of the magnetic field. Then we just substitute into the equation, and then we just calculate it. You will get 1.05 exponent -3 Newton, where the direction just into the page. Okay, number 5b, by giving you alpha particles of charge 2e positive, okay, mass also given here, are emitted from a radioactive source at a speed of, okay, this is V, okay, this is our Q. What magnetic field strength will be required to bend them into a circular path of radius R given to be 0.25. So by giving you the total charge, okay, and then the mass, also the speed, they ask you to find the magnetic field strength, which is B, by giving you R, the radius, to be like this. Okay, so how is it? So for question B, this is the way. So we are talking about a circular motion where FB equals to FC. So FB equals to QVB sin theta and FC equals to mv squared over R. So remember, the particle is moving in a circular path. Okay, we are talking about circular motion. So QVB sin theta equals to mv squared over R. So sin theta is the angle between V and B, where V and B, they are perpendicular to each other. So giving you sin 90. Sin 90 equals to 1. Okay, and then V and V squared cancelling each other. What do we have now? Just V only. Okay, so by rearranging the equations, you will get this. B equals to mv over br. M given already, V also given. Oh, sorry, this one is not B. Suppose the Q. Sorry, my mistake. That one is Q. Q, okay. So this is Q, and Q is positive 2e, isn't it? Okay, so 2 times by E, and then this is the radius given. So that you will get B equals to 1.32 Tesla. Okay. Okay, so let's continue by question number 6. Okay, what do we have? In this question, they just give you a helium ion where the charge is positive 2e and its mass is 6.6 exponent -27 kilogram. It's accelerated by a voltage of 2400 volt. Okay, what do we have? This is Q. Oh, I need to change the color first. I like the red one. We can see it clearly, isn't it? Okay, so what do we have? This is Q, and this is mass M, and this is our V, voltage, capital V, right? So the accelerated ion then move into a perpendicular uniform magnetic field of magnitude 0.24 Tesla. So this is our B. Determine the radius of circular path of the, okay, they ask you to find R, also the period. Okay, so again, charge of electron given is 1.6 exponent negative 19 coulomb. Alright, so according to this situation, they just give you Q, M, voltage, also B. They ask you to find R and T. Okay, so in this case, we need to use this principle, isn't it? FB equal to FC, where FB is QVB sin theta equals to FC, which is mv squared over R. So V and V squared cancel each other. Sin theta equals to 1 because they are perpendicular to each other. So theta is 90. Sin 90 equals to 1. So by rearranging the equations, you will get this. Okay, so to calculate R, M given, Q also given, B also given, but V is not given here. This is small v. Small v representing velocity. But the values given now is not small v, it's capital V, which is voltage. So we need to find the speed first. So according to the principle of conservation of energy, electrical potential energy equals to kinetic energy. So electrical potential energy equals to QV. And kinetic energy equal to half mv squared. See, these two V, they are different. Capital V make it sharp. Small v make it italic, representing speed or velocity, okay? So for this, by rearrange the equations, you will get speed equal to square root of 2qv over m. So this capital V representing voltage. So substitute Q is 2E, V given is 2400 volt, and mass also given, so that you will get V. By getting the speed now, V, we just substitute into this equation again, and then you will get the answer. So the radius getting now is 4.14 exponent negative 2, and from this they ask you to find the period. So period equals to 2 pi r over V. So r getting before, substitute into this equation. V also calculated just now, substitute here, and then you will get the period. Okay, normally the question given just be like this. They are related to each other. By getting wrong for V, of course lah, your R also wrong, also the period. They are related to each other. So please be careful for the calculation, also for the substitution, okay? Alright, next question is number... Okay, so question number 7. Okay, figure below shows two straight conductors, which is K and L. So this is K conductor and this is L conductor. P is the midpoint. So P is a midpoint between K and L. So determine the current through wire K. Direction of current through wire K is shown. Okay, so the current on wire K now just directed upward. Okay, magnetic field resultant at P is 0. So state direction of current on wire L. Okay, so by giving you the direction of current on K and the resultant of B at P equal to 0, they ask you to find the direction of current on L. Okay, so based on this current, by using our right hand grip rules, so the thumb finger are representing the current and this forefinger representing our B. So B at this side just directed out of page, and at this side B just directed into the page. So for K, B of K now is out of page here, and at P here just directed into the page. Okay, so now the keyword given now, resultant at point P equal to 0, means that the second B must be in opposite direction of the first B before. Okay, so the first B just directed into the page. So to cancel out this B, the second B should be out of page. So to have this, okay, the B produced by the second wire should be like this. So at this part, okay, the direction of B, it must be directed out of page, so that you may cancel out B by the first wire before. Okay, so to have this, to make it out of page here and into the page here, based on our right hand grip rules, again the current, it must be directed upwards, so that B at this side just directed out of page, and at this side it just directed into the page. So out and in, they may cancel each other. By cancelling each other, then the resultant on P just equals to 0. So to have this, the current must be directed upwards. So this is the way how to explain it. Okay, so from the upper view, by having a view from this side, from the upper view, we can see the pattern just be like this. So these two B, they need to oppose each other, so they are cancelling each other, giving you 0 resultant at point P. Okay, so this is B of the first wire, K wire, and this is B of L wire. Okay, so opposite direction, they may cancelling each other. Okay, don't be confused. What do I mean by this figure? Okay, this is BK lah, at point P, and this is BL at point P. See, they are opposite in direction. Okay, that is why they are cancelling each other. Okay, because P is a midpoint, so I think the current still the same there, so that our B, K and BL also equal in magnitude, but opposite in direction, they are cancelling each other, giving you zero resultant. Okay, so how to explain that? Direction of current on wire L same as the direction of current in K wire, alright, which is upwards. And then for the second part, state the direction of the force exerted on K wire caused by the current that flows through L wire. Okay, by getting current to be upward here, then they ask you to find the force exerted on K caused by L. Okay, so remember, equal direction of current, they will repel each other, isn't it? So that the force on K, it must be directed to the left, because to repel each other, the force must be directed in this direction, isn't it? So they are repelling each other. Sorry, equal current, they are attract each other, isn't it? Okay, sorry, my mistake. Okay, sorry, again, the current of K just directed upward, also for L, the current is directed upward, so equal direction of current, they will attract each other. Okay, so the force must be like this lah, to attract each other, so that the force exerted on K, it must be directed to the right. Okay, so here, how to answer that? Current direction is the same, so that so they will attract each other. So FK directed towards L or to the right. Alright, see, so this is the way how to answer the question lah. Okay guys, so now let's continue by question number 7B. Alright, so what do we have now? The figure above shows a long straight conductor, which is X. So this is our straight conductor carrying a current of 6 amperes. So the current through this cable or conductor is 6 amperes. A rectangular metal frame PQRS suspended, okay, with PS is 3 centimeter from X. Okay, so the sides of PQ and QR is 4 centimeter. And 11 centimeter. QR is 11 centimeter. Okay, the length of each side here lah. PQ is 4, QR is 11 centimeter. Alright, then a current through this rectangular conductor now is 3 amperes. So the conductor X and the metal frame PQRS are in the same plane. So calculate the force on the wire PS and wire QR. Hence, calculate the resultant force on PQRS and determines its directions. Okay, so based on this, seems like PS just in parallel with X. Also QR just in parallel with X. So according to the parallel conductor we have discussed before, when the current flow through both wires just in the same direction, they will attract each other. Okay, while when the current just in opposite direction, they will repel each other. Okay, so this is the current flow through the rectangular coil lah. So the current given just be like this. This is the current. Okay, seems like PS and X, they are parallel to each other, but the direction of current just in opposite direction, isn't it? So they will repel each other. So for this part, the repulsive force exerted on it, which is FPS. Okay, F on PS by X. At the same time, the force also exerted on QR, which is in parallel with X. But according to the situation, the current through both wires now just the same, which is downward and downward, isn't it? So they will attract each other. So the force exerted on QR is FQR, which is by X. So seems like on this rectangular we have two different forces which is exerted on PS, also on QR, and they are in opposite direction. So we need to know which values is greater now, because the rectangular coil or conductor will move in that direction. Okay, alright, so we just calculate one by one lah. First, FPS by X. So we are talking about these two parallel wire. And secondly, we just calculate FQR, which is the force exerted on QR, which is caused by X. Again, they are parallel to each other. Okay, so this is the way how to answer the question. Okay, before that, this is the hidden info. Current in X and PS, they are opposite in direction. So we are talking about the repulsive force. So based on that, the force exerted on PS just directed to the right. While current in X and QR, they are in the same direction. So we are talking about an attractive force. So that the force exerted on QR just directed to the left. Okay, based on that diagram. Okay. Alright, so we just calculate one by one. First, we just calculate F on PS. F on PS equals to ILB sin theta. So remember, we are talking about PS conductor. So the current should be PS current. Okay, but the magnetic field strength exerted on it should be the other one, isn't it? Which is by X. So FPS equal to IPSL BX sin theta. Okay, so again, theta is 90 degrees. Okay, because L and B, they are perpendicular to each other. So the angle is 90 degrees, sin 90 giving you 1. Okay, alright, so IPS is the current through PS conductor. Length given already. Bx equals to mu naught Ix over 2 pi r. Okay, so we are talking about the current through X wire lah. Okay, so we just substitute all the values. This is I through PS. This is the length of PS. And then mu naught just a constant. This is Ix. Okay, and then 2 pi r. R is the separation between X and PS. They are separated by 3 cm. Convert it to be in meter. And then sin 90. Because the angle between L and B equals to 90 degrees. Giving you the answers to be like this, which is to the right, based on the diagram. Okay. By doing the same thing, we just calculate the force exerted on QR. So F on QR equals to IQR L B sin theta again. So remember, on QR wire, the current should be QR. Then B exerted on it should be B by others wire, which is X. Okay, again, Bx equals to mu naught Ix over 2 pi r. So this is the equation. Again, IQR given 3 amperes. Length of QR is 11 centimeter. Convert it to be in meter. Mu naught just a constant. Ix is the current through X wire, which is 6 amperes. 2 pi r. So r is 7 centimeter. So the separation between QR and X, they are separated by 4 plus 3, isn't it? Which is 7 centimeter. Convert it to be in meter. Again, the angle is 90 degrees because L and B, they are perpendicular to each other, giving you the answers now to be like this, which is directed to the left. And then for the second question, they ask you to calculate the resultant. So to calculate the resultant, resultant force equal to FPS plus FQR in vector. So FQR just directed to the left, it must be negative. So we just substitute the magnitude for both forces. Then you will get the answer where the answer getting out is positive, means that the resultant just directed to the right. Okay, so remember, to calculate this, we need to refer to the diagram. Okay, it's all about the direction, is very important. So again, different direction of current, they will repel each other. The force on PS just directed to the right, and then downward and downward, equal direction of current, they will attract each other. So the force exerted on these two wires, just the blue one. So on QR, the force just directed to the left. So remember, this is vector. Before we just calculate the magnitude, we need to know the direction, because in calculating the resultant, it's very important to know the direction. Okay, all right, that is for question number 7B. Okay, next, question number 8. What do we have? A rectangular shaped coil with sides 5 cm times 4 cm is placed vertically in a uniform horizontal magnetic field of 0.1 Tesla if the coil has 10 turns and the current flowing through the coil is 2 amperes. Calculate the torque acting on the coil when the plane of the coil is 30 degrees to the field. What is the maximum torque? Okay, so as usual, we need to identify all the infos given. What is it? Okay, first, 5 times 4. What is that? That is the area. Okay, but remember, centimeter giving you centimeter squared. We need to convert it to be in meter squared for any calculation, okay? And then place vertically in a uniform horizontal magnetic field. Alright, so this is B. If the coil has 10 turns, so this is N. And the current flow through the coil, okay, this is I current. So they ask you to find torque, okay, when the plane of the coil is 30 degrees. Okay, what angle is that? Is it alpha or theta? Okay, according to this, the angle given are between plane and the field. Plane and the field is alpha because the angle between vector of area and B is theta. Okay, so be careful. This is one of the trick lah. The angle given is not theta. That one is alpha. Okay, so we need to find theta in calculation. Okay, what is the maximum torque? Okay, so this is the situation. Okay, this is the coil and this is our magnetic field. Alright, so the coil just rotating now. So for this position, the angle given is 30 degrees between the coil and B. So remember, that is alpha, it's not theta, because alpha should be the angle between vector of area and B, where vector of area just perpendicular to the surface. Okay, so we need to find theta. Theta equals to 90 minus 30, giving you 60 degrees. Okay, so by using the torque equation, torque is equal to niap sine theta. So N given is 10, I given is 2, A given is, okay, so remember we need to convert it to be in meter squared, so that we have 10 to the power -4 here. Okay, and then B given is 0.1 and the angle is 60 degrees. So many students done mistake here by taking the angle to be 30 degrees. So be careful with this, okay? So that you will get the torque is 3.46 exponent -3 Newton meter. And they ask you to find the maximum torque. So remember, for any maximum torque, the value of sin theta should be maximum. So sin theta just between 0 until 1. The maximum value is equals to 1, which is sin 90, isn't it? Okay, so by substituting sin theta equals to 1, and then we just substitute N, I, A, and B given before, then you will get the maximum torque, which is 4.0 exponent -3 Newton meters. Okay. Okay, next question, which is number 9. An electron with a kinetic energy, okay, so this is K, the kinetic energy is given, enters a region between two parallel horizontal metal plates. The distance between the plate is 15 centimeters. So this is D, the separation between plates. And the potential difference across the plates is 120 volt. That is potential. The upper plate is negative potential and the lower plate is positive potential. So remember, upper plate is negative in charge and lower plate is positive in charge. Okay, so show on a diagram the direction of the applied magnetic field so that the electron move undeflected parallel to the plates. Calculate the magnitude of this magnetic field strength, okay, by giving you the electron of charge, the charge of electron, also the mass of electron. Okay, so based on this, okay, remember upper plate is negative, so we just draw the figure to be like this. The upper plate is negative and the lower one is positive. Based on that, our E just directed upwards because electric field always start from positive pole towards the negative pole. So this is our E. Okay, now we are talking about an electron. So electron is a negative charge. The electron just move through this area. So remember, as a negative charge, it will be attracted by the positive plate, isn't it? According to the ideas introduced by Mr. Coulomb before. So we are talking about the electrostatic force. So in this case, negative charge attracted towards the positive plate. So the force exerted on the charge just directed downward, which is Fe. Okay, based on that, the object will be deflected to be downwards. So to ensure that the motion just be on a straight line to be like this, we need to cancel out the force, isn't it? So we need to have another force which is against Fe. So it must be directed upward. So in this case, we need Fb to cancel out Fe. So when the magnitude of Fb and Fe equal to each other, they are cancelling each other so that the motion of the particle just be on a straight line. So to have that, to have Fb to be upwards, Okay, we need to ensure that the direction of B here should be correct. So by using our pumps rule again, V is directed to the right, FB is upward. So this is a negative particle, so we are referring to our back hand, isn't it? Okay, by using our by using our pump rules, the pump rules, okay, this is our hand. This is a four fingers representing B, and this is our thumb finger representing V. Okay, so this is V, and this is B. B just directed upwards. Okay. Sorry, it's not B. We need FB. Sorry, wrong figure. So our hand should be like this now. How to draw the hand? Okay. In 3D, this is our four fingers, and this is thumb finger. Okay. So this is V, and our F just back hand, isn't it? Which is directed upward. This is F. So by using our pumps rule, which is the right hand's rule, okay, our F just directed upwards, V just directed to the right, so that our B must be directed out of pitch, isn't it? This is B, based on 3D axis lah, which is X, Y, and Z. Okay, so F just directed upwards, V just directed to the right, so that B just directed out of pitch, which is positive Z. That is why the pattern is now just in dot pattern. Dot pattern representing that our B just directed out of pitch. So by having B which is directed out of pitch, then our FB just directed upward. So equal in magnitude, FB and FE just cancelling each other. So no more force exerted on the particle, then the object just move on a straight line. So this is the principle. Okay, so remember, to ensure the motion just be on a straight line, FB and FE should be cancelling each other, so that the direction of B is very important to ensure the FB against FE. Okay, all right. And then for the second question, they ask you to calculate the magnitude of this magnetic field strength. Okay, so to calculate the magnetic field strength, okay, using V equals to E over B. Okay, in velocity selector, the question is V equal to E over B, so that B equal to E over V. So E equals to V over D, where V is the potential between plates and D is the separation between plates, isn't it? Given already. But now the speed is not given here. Then we need to calculate speed first. How do you calculate speed? By using the principle of conservation of energy, where the potential energy equals to the kinetic energy. So what type of potential energy here? Electrical potential energy equals to kinetic energy. So electrical potential energy equals to QV. So Q is the charge, V is the potential supply. Okay, equals to K, which is half mv squared. So two different V, capital V or sharp V representing voltage, small v which is an italic symbol representing speed. Okay, so by rearrange the equations, you will get that speed equals to square root of 2qv over m. So 2 just a constant, q also constant, which is the charge of electron. This is the potential supply, which is 2000, and this is the mass, okay, of electron given already. Substitute and then you will get the speed. By getting the speed, and then we just substitute into the equation before here, and then you will get the answer. So the magnetic field strength is 3.02 exponent -5 Tesla. Okay, next question number 10, which is our last question. Okay, again, it's about the mass spectrometer. We are talking about the velocity selector and evacuated chamber. Okay, so a beam of hydrogen ions from a discharge tube contains the isotopes of hydrogen and deuterium. Okay, the beam enters a velocity selector which consists of a magnetic field B given here. This is B1. This is B1, which is in the velocity selector, and the electric field also given here. This is E, which are mutually perpendicular to each other. So B and E, they are perpendicular to each other. That is normal in any velocity selector. Okay, ions that emerge from the velocity selector enter a region of uniform magnetic field B. Okay, so this is B2, which is in the evacuated chamber. Okay, remember we have two different parts, which is the velocity selector and evacuated chamber. So B2 just in evacuated chamber, we just have one field only, which is B. Okay, in the velocity selector, we have two different field, which is B and E. Alright, so this is to ensure that the motion of the particle just on a straight line. But in the evacuated chamber, we just have B only. Why? Because we have to deflect the particle to be catched by the photographic films, so that we may measure the radius of the circle. Then we may identify what type of particle is that, isn't it? Okay, so based on that, calculate the velocity of the ions that pass through the velocity selector undeflected. Okay, so undeflected, this is the keyword which is in velocity selected. Okay, because we have B and E producing FB and FE, which is in opposite direction. They are cancelling each other so that the object just move on a straight line without any deflection. Okay, so the velocity of the ions, okay, this is the velocity in velocity selector. Alright, and then the radius of semicircular path of the ion. Alright, so this is in the second part, which is in evacuated chamber using B2. Okay, alright, so by giving you the charge of proton or electron, okay, they ask you to calculate again the velocity in the velocity selector, and then the semicircular path of the ion, which is hydrogen and deuterium. Okay, how is it? Okay, first, in any evacuated chamber, in any velocity selector, we know that V equals to E over B. E and B given already, substitute here, and then you will get the answer. So this is the speed of the particle in the velocity selector. Okay, and then in the evacuated chamber, we are talking about deflection only, so that we are talking about a circular motion. So FB equals to FC. Alright, FB equals to QVB sin theta, FC equals to MV squared over R. Then, by rearrange the equations, okay, V and V squared cancelling each other. Sin theta equals to 1 because theta equals to 90 degrees, because V and B, they are perpendicular to each other. So that you will get R equation, which is MV over QB. So that for the hydrogen, okay, we just substitute the mass of the hydrogen given already, the speed also calculated just now, and then this is the charge of hydrogen, and this is the magnetic field in the evacuated chamber, in the last part there. Alright, so that you will get the radius is 0.104 meters. Okay, that is for hydrogen. And then by doing the same thing for the deuterium, okay, again, this is the mass, this is the speed in the velocity selector. Okay, okay, so remember the velocity in the speed in the velocity selector now become as the initial speed for the evacuated chamber. Alright, that's why we are taking the same values of V inside the velocity selector. Okay, and then this is the charge of the particle and deuterium, and this is the magnetic field strength in our evacuated chamber, so that you will get the answer is 0.209 meters. Okay, so remember in this case the charge still the same. What do we have now? The difference just in mass only. Why? Because in hydrogen we just have one proton, isn't it? But in deuterium we have one proton and one neutron. That is why the mass are different now, but the charge still the same, because by having one proton and one neutron, neutron still a neutral particle, so that the charge still caused by the proton, isn't it? Same as before. That is why the charge still the same. Okay, alright, so this is the way how do we answer question number 10. Okay, now let's complete the objective question. Okay, number 1. A metal rod carrying a current I is placed perpendicularly to a uniform magnetic field B as shown in the diagram below. So what do we have? Okay, this is our B, which is directed to the page, and this is the circuit. Alright, so this is our metal rod carrying a current. The current just directed to the right. So B just directed into the page. They ask you to find the force exerted on the metal rod now. Okay, so again, by using our pump rules, okay, so this is the hand, and this is our 4 fingers, and this is our thumb fingers. Okay, in 3D again. This is X, this is Y, and this is Z. Okay, so our B just directing to the page. This is our B, which is directing to the page, and following the negative Z axis. And this is our I just directed to the right, which is equal to positive x. This is negative z direction because B just directed into the page, isn't it? So based on that, by using our FBI, so this is our F. So F now just parallel to the y-axis, which is positive, isn't it? Okay, so the answer should be upwards lah. So the answer should be A. Okay, all right. Next, second, two long and straight copper wires are placed parallel to each other. A constant current flows in the same direction. So we know that for the same direction, they will attract each others, isn't it? So the answer is D. See, it's too simple, kan? Physics is so easy actually. Don't worry. And lastly, the strength of the magnetic field at the center of the solenoid can be changed. Which of the following rows correctly describe what happened to the strength of the magnetic field when the current and number of turns increase? Okay, the question is B equals to mu naught n I or mu naught n I over L. So by increasing the current, what happened to B? Of course, increase. By increasing the number of turns, what happened to B? Also increase. So the answer should be increase and increase. So that B is the best answer. Okay guys, so we have complete tutorial. For any problem, let me know. You may ask me through the telegram groups. Okay, so by the next class we just continue by chapter 5. Okay, and don't forget to check your answer and compare with my answer. Any problem, any confusion, let me know. Okay, so all the best, good luck, see you guys, thank you, Assalamualaikum.